Hello everyone and welcome to another episode on this very channel. In today's lesson, we shall be looking at the classifications of PDEs. If you haven't yet subscribed to the channel, kindly hit on the subscribe button for me. So without wasting much time, let's start. PDE or partial differential equation can be classified according to their order. So we have the first one is order. It can also be classified according to their homogeneity. Under the homogeneity, we shall be looking at the homogeneous and non-homogeneous PDEs. PDEs can also be classified according to their linearity. And under the linearity, we shall be looking at the linear and then non-linear. So these are the classifications that we want to look at in today's lesson. These are not the only classifications of PDEs. We can also classify PDEs according to their scalar or systems of equation. We can also classify PDEs according to their evolution or stationary. That is whether it depends on time or not. As I said, for the purpose of today's lesson, we are going to concentrate our focus on the linearity, homogeneous, and then the order of the PDE. So let's start with the linearity. The linearity. So a PDE is said to be linear if it satisfies the following condition. If it would satisfy the following conditions. So these are the conditions that a PDE must satisfy in order for it to be a linear PDE. Other than that, it is not linear, but rather non-linear. So if one of these conditions fails, then that PDE becomes a non-linear PDE. And if all these conditions are met, then the PDE becomes a linear PDE. So these conditions are the same for an ODE to be a linear. Other than that, it is a nonlinear ODE. So let's go through the conditions. So the first condition says that the dependent variable and or its derivative occur to the first degree only. And I believe that at this very point, you know what the degree is. So what we are saying that for the PD to be a linear, the dependent variable, and we know that the dependent variable is this. So the dependent variable and or its derivative must occur to the first degree only. So we have the dependent variable and then its derivative, we can take it with respect to x or we can take it with respect to what? Y. We can also take the derivative with respect to 2 times, with respect to y, 2 times, 3 times, and so on. So what we are saying that the dependent variable and its derivative must occur to the first degree only. So for the PD to be a linear, then it must occur to the first degree only. We should not have something of this form, u squared x or u power 3 y. If you have a PD and then you have this within, then it means that that PD is not a linear PD, but rather a non-linear PD. So that's the first condition. Now let's look at the second condition. There is no product of the dependent variable and or its derivative in the equation. So these are dependent variable. We should not have a product, multiplication of the dependent variable and or its derivative in the equation. So it means that within the equation, we shouldn't have something of this form, the dependent variable and then its derivative. We shouldn't have something of this form, the product of the derivative. We should not have something of this form, x, and so on. So this is what the second condition. There's no product of the dependent variable, which is u and or its derivatives in that equation for it to be a linear. When we have something of this form in the equation, then that PDE is not a linear but rather a non-linear PDE. Now let's look at the third condition. There is no transcendental function of the dependent variable and or its derivative. So we are talking about transcendental functions. When we talk about transcendental functions, then we are looking at the length. Then we are talking about the exponential functions. So let's say line, okay, the exponential functions. Then we are talking about the trig ratios such as the sine, the cos, the tan, and so on. So what we are saying is that there is no transcendental function of the dependent variable. So it means that this transcendental function, we shouldn't have something like ln u. Neither should we have something like ln us. Now we shouldn't have. The moment you have ln u or ln us or ln uy, then that PDE ceases to be a linear PDE but rather a nonlinear PDE. So here we shouldn't have something like es within u, the transcendental function on the dependent variable. We shouldn't have that. The moment you have something of this form or this, it becomes a nonlinear PDE. Then we shouldn't have something like sin u or sin ux or sin uy and so on. The moment you have something of this form, then that PDE ceases to be a linear PDE but rather a nonlinear PDE. The same thing applies to the cos, the tan, and so on. Good. So these are the conditions that a PDE must satisfy in order to become a linear PDE. Other than that, it is what? A nonlinear PDE. So in looking at that, we are going to consider the following examples here, the following PDEs here, and then we are going to classify them according to linear and then nonlinear PDEs. So let's look at the first one. So let's look at the first example. Ux plus 3uy is equal to 2. So you can see that the first condition is satisfied. The dependent variable and its derivative occur to the first degree only. So we have the first degree only. The second condition too, there is no product of the dependent variable and or its derivative. There's nothing like u, there's nothing like this. U, ux, or u, uy in the equation. So the second condition is also satisfied. Then let's look at the third one. There is no transcendental function. So you can see that there is no transcendental function. So this PDE is what? A linear PDE. Very, very easy to identify them. Then let's look at example 2. We have the second partial derivative of the function with respect to what? X plus 3 times the partial derivative of the function with respect to x and y plus y uyy is equal to what? Sin xy. So we can see that the first condition is also satisfied. There's the dependent variable and its derivative occur to the first degree only. So you have first degree. There's nothing like u power 2, u power 2, u power 3. Nah, there's nothing of this form. The second condition, there is no product of the dependent variable and or its derivative. There's nothing like the dependent variable multiplying the derivatives. There's nothing of that form. Good. Let's look at the third one. There is no transcendental function of the dependent variable. There is no transcendental function of the dependent variable. We have a transcendental function here, sine, but it is not on the dependent variable, but rather it is on the independent variable. So this is also a linear PDE. If this part was to be sine ux or sine u, then it would have been nonlinear. But because it is on the independent variable, it is what? A linear PDE. So let's look at the third example. Looking at this PDE, let's go through using the conditions. The dependent variable and its derivative occur to the first degree. So you can see that this does not occur to the first degree. It occurs to the second degree, third degree. So this is what? Nonlinear PDE. Very, very simple to identify. And if one of these conditions fail, the PDE becomes a nonlinear. Very, very simple. Now let's look at this. We have ux degree 2 plus uy degree 2. So you can see that the first condition is not satisfied. So this PDE becomes what? A nonlinear, because we have the dependent variable and its derivative does not occur to the first degree. It occurs to the second degree. So this becomes a nonlinear. Then let's look at this. We have ln ux, a transcendental function on the derivative of the dependent variable. So where is it? There is no transcendental function on the dependent variable and or its derivative. So this is the transcendental function. and then the derivative of the dependent variable. So this prevents it to be a linear PDE, but rather a nonlinear PDE, so nonlinear. Now let's look at this. We have this sin u. Sin is also a transcendental function, and it is on the dependent variable. So this makes it what? A nonlinear PDE. So we have nonlinear. Then let's look at this. We also have this equation. We have an exponential function which is part of the transcendental function. But this exponential function, which is the transcendental function, is not on the dependent variable or its derivative, but it is rather on the independent variable. So this is what? A linear PDE. This makes it what? A linear PDE, because this is not on the dependent variable or its derivative. If we were to have something of this form, EU or EUX, then this would have been what? Non-linear. Very, very easy and then simple. Let's look at the other classification that is based on the order. The order of PDE is the highest order of the partial derivative that appears in the equation. So with the order, we are looking at what? The highest derivative within that equation. So let's take it that you have a PDE, and in that equation, the highest order is k. Then the equation is said to be what? Order k. Very, very easy and then simple. I said that with the order, we are looking at what? The highest derivative, the highest partial derivative in that particular equation. So we are going to consider the following PDEs, and then we classify them according to the order of PDE. So looking at the first example, we have del u, del x plus del u, del y, or taking the first partial derivative of the function u with respect to x plus taking the partial derivative of the function u with respect to y. We are taking what? The first partial derivative. So this PDE is what? A first order PDE, first order. And then the order is order 1. Very, very easy. It is a first order PDE, and the order is what? 1. Very, very easy and then simple. Let's look at this one. We have the square u, the x square plus 3 times the square u, the y square. We are taking the second partial derivative of the function u with respect to y, the second partial derivative of the function u with respect to y. So the highest derivative is what? 2. So this equation is what? A second order. And then the order is what? 2. We are taking the second, so the order is what? 2. Let's look at this one. So what is the highest derivative here? This one, we are taking the second partial derivative with respect to x. We are taking the second partial derivative with respect to y. We are taking the third partial derivative of the function u with respect to what? X, y, and z. So the highest derivative is what? This part, that is 3, the third partial derivative. So therefore, this equation becomes what? A third order PDE. So we have third order PDE. And then the order is what? Order 3. So it is a third order PDE, and the order is order 3. But this one is called the degree. Take note, this is the degree, and then the order is what? 3. Now let's look at this. We have the first partial derivative of the function with respect to x, the third partial derivative, we have the second partial derivative, and then we have the fourth partial derivative. This was the fourth partial derivative. So the highest derivative in this equation is what? 4. So this PDE is what? A fourth order PDE. So we have fourth order PDE. And then the order is what? Order 4. The order is order 4. Now this is the degree 6, and then this is what? The degree 5. So the highest degree is what? Degree 6, but the highest order is what? Order 4. take note of the difference. There is difference between the degree and then the order. Now let's look at the last one. We are taking the second partial derivative of the function with respect to t time, and then we are taking the second partial derivative of the function with respect to what u, and this is equal to a function of x and then t. So the highest derivative is what 2. So we have 2, but the degree is what 4. So we have a second order PDE, and the order is what? Order 2. Very, very easy and then simple. Let's look at the other classification that is based on homogeneity. So we are looking at the homogeneity of PDE. So as I said, under the homogeneity, we have the homogeneous PDE and then non-homogeneous PDE. When do we say that a PDE is homogeneous? A PDE is said to be homogeneous if it does not contain any function of the independent variable alone. It does not contain a function of the independent variable standing alone, but rather it contains either the dependent variable u and or any of its derivatives. So this means that when you have a PDE, and in that PDE, we are not expected to find a function of the independent variables standing alone. So if our independent variables are x and then y, we are not expected to find a function of x standing alone or a function of y standing alone, but rather we are expected to see something like the dependent variable u and then any of its partial derivative. If that happens, then we can say that that equation or that PDE is an homogeneous PDE. Now, what about non-homogeneous PDE? That is the opposite of it. So when you have a PDE and in that equation you have a term, there is a term in that equation, and that term is a function of the independent variable alone, then we can say that that equation or that PDE is a non-homogeneous PDE. You have an equation, and then in that equation you have a particular term in that equation, and that term is a function of the independent variable standing alone. Then we can say that that PDE is what? A non-homogeneous or inhomogeneous PDE. So let's take it that you have in terms of two independent variables x and y. So this is it, a homogeneous PDE. So with these two, when you have a PDE and then this PDE is in terms of two independent variables x and y, and then this PDE is having a function that is in terms of the independent variable x and y, then we can say that that PDE is non-homogeneous PDE. You can see that with this one, we don't have any function that is in terms of what? The independent variable x and y, and therefore this PDE is homogeneous. But with this one, we have a function that is in terms of what? X and then y. So if this g at xy is equal to 0, then we have a homogeneous PDE. Very, very easy and then simple. Let's look at these examples of PDEs on the board, and we are going to classify them according to homogeneous and then non-homogeneous PDE based on the explanation. So we have the first one, ux plus uy is equal to 0. Do we have a function that is in terms of x and then y? You can see that we have none. Since we don't have anything of that form, this becomes what? A homogeneous PDE. Very, very simple. Just look out to see if we can have a function of the independent variable standing alone, and then you are good to go. So we have uxy plus uxx is equal to uy. Do we have a function that is in terms of the independent variable x and y standing alone? We don't have. So this still becomes what? A homogeneous PDE, because we don't have any function of x, neither do we have any function of y in this equation. Now let's look at this. We have uxx plus uyy is equal to x. Do you have any function of x, or do we have any function of y? You can see that we have, yes, a function of what? The independent variable x. Because of this x, this PDE becomes what? A non-homogeneous PDE, non-homogeneous PDE, because we have a term that is a function of the independent variable standing alone. So that is it. Now let's look at this. We have UUX plus XY UY is equal to E exponent X and then Y. Do we have a function or a term that depends on the independent variables alone? Yes, you can see that this term is a function of what? X and Y. And therefore this PDE becomes what? A non-homogeneous, because we have a term that is a function of the independent variable X and Y because of that. Now let's look at this. You can pause the video and then you try your hand on this. Is this homogeneous or non-homogeneous? You can see that we don't have any function that is in terms of the independent variable standing alone. We have UUX, we have the independent variable X and Y, but these two independent variables are not standing alone. They are attached to the partial derivative with respect to Y, and therefore this becomes what? A homogeneous PDE. If it was to be like this, then it will have become what? Non-homogeneous. But because this is attached to the partial derivative with respect to Y, it becomes what? Homogeneous. Just take note of the difference. It becomes what? Homogeneous. Now what about this? We have UXS plus UYY minus UY is equal to sine S. We have a function that is in terms of the independent variable X, and therefore it makes this equation non-homogeneous. Very, very easy and then simple. This brings us to the end of today's lesson. See you tomorrow. Bye bye.